In this section, we're going to introduce the idea of a semaphore. So last section we saw the idea of a mutex. Mutex was basically a way to ensure that some set of threads, only one of them right at a time can access a particular resource, right? So there's maybe one global resource out there and only one of them is allowed to mess with it at a time. Semaphores are a little bit of a generalization. So in semaphores are typically represented as an integer that is supposed to be counting up a number of resources, right? So instead of just saying, oh, something like a mutex would be perfect, right, for the critical section problem because, hey, only one person is allowed to be in a critical section at a time. But what if you had something a little bit more general? What if you had something like, oh, I have, n type of a resource, right? Maybe you have stuff like, oh, I could, print to, different pinners, right? Maybe I have 3 pinners. Well, then a mutex doesn't really work, right? Because you want to make sure that only one person is using a printer at a time, but you also want to say, hey, it's fine for me to have, 3 people working on this at the same time, right? They just have to have different printers. I don't want to just say, oh, one person can print to one of those printers at a time, right? I want those things to be things that I can use in parallel. Well, that's what semaphore is doing because a semaphore is ultimately about counting the availability of a particular resource type, right? So you have this type of resource, printers, there's 3 of them, right? You can model that with a semaphore that's set to 3. So semaphores are an integer value, right? They're not just a Boolean true or false, not just 0 or 1, it's an integer. The value of a semaphore variable, right? We'll have semaphore variables in our program, is a number of that resource type that is available to the outside world to use, right? So then what happens, right, is let's say your program is running, there's 2 ways to interact with a semaphore. One is a wait, one is a signal. A wait is basically going to say, okay, I'm going to go to that semaphore, that integer value, and see if it's positive. If it's positive, that'll mean that there is a particular resource of that type available, right? There's a printer out there that I could print to, right, if it's a positive value. If that number looks like a 0, right, the semaphore is a 0, that implies that there are no resources available. For certain types of semaphores, there'll actually be some additional meaning too behind negative values. A semaphore can be negative if really it's saying like, hey, this is how many people are waiting to use a printer, right? So if you have -5, that means you have 5 people waiting around to do a print job or something like that, right? Of one of those 3 printers that are available. So wait is going to be our first command, basically to say, can I get a hold of one of those resources, right? Because here it's a semaphore. There may be multiple things. It's not a mutex. Mutex is about just preserving, access to one particular thing, right? Making sure only one person is in the critical section. Semaphore is about counting the number of resources. All right, so the second operation we have there is signal. So signal is saying, okay, I've been using this resource as represented by a semaphore, now I need to release it back, right? So basically it's the equivalent of doing a plus plus on that number, right? You're saying, okay, there's one more thing that's available, now somebody else can go and use it. So our wait and our signal, right, hopefully these are atomic operations. These are going to be our basic ways, right, to interact with that semaphore variable in our program. So on the right-hand side, right, we have our 2 kind of models of how these things will look. First of all, right, we have our wait. So wait is going to look at the S variable, right? And basically, that variable isn't positive, right? Well, it's negative, right? That means, well, hey, I don't have any resources, right? Because that variable, right, should be counting up the number of available resources. So if it's not positive, well, then how can I, move forward? How can I go and do stuff, right? I can't. I need to make sure that S variable is positive, right? That semaphore is positive because that implies I have a resource available, and then I'll do S minus minus to say, okay, yeah, hey, I'm going to use this now, right? And then this function exits out, and somebody else can continue on with their code, right? If it ends up being that number was not positive, right, a positive 1 or greater, then basically it'll just sit there at that wait, right? So this is going to be busy waiting. So notice the semicolon at the end. Semicolon at the end, right, is basically saying I have a loop that's running, it's continually checking, but it's not doing any actual work, right? So it's just busy waiting until I have that S is positive, and then it can move forward. So that's kind of how we could think about wait being implemented. All right, so signal, right, is on the flip side. Signal basically says, okay, for S, I'm done working with that resource, so let me just do a plus plus on it to increase it by 1 and say, yeah, there's somebody else can use it. All right, so that's our basic idea of a semaphore, right? It's a generalization of a mutex where we can have more than one resource being guarded. So let's take a look at using semaphores to solve 2 problems. The first is going to be the critical section problem. The second one is going to be, it's something a little bit new. It's going to be about forcing order of execution. So the first thing we have here, right, is our critical section problem. We've talked through this, right, for a few things now. So this basically is going to be very simple to how you do it with a mutex. Here, right, we're saying, oh, critical section problem means that for a set of threads, only one thread can be in this region at a time. Well, because of that, what we want is we want a global semaphore out there that's just set equal to 1, right? 1 is the number of resources available, right? One person is allowed to be in the critical section at a time, right? We don't want to set it to some larger value, right? If we set it to something like 10, what that would imply is, oh, up to 10 threads can be in the critical section at a time, and that doesn't really solve our problem, right? We want to make it unique. We want to make it exclusive. So we'll create a semaphore and set it equal to 1. And then we have our loop, right? So in our loop, basically what we say is, okay, I got to wait around, right, for my resource to become available, right? I can do a wait, right, on that lock, right, on that semaphore, right? The variable is called lock. It's of type semaphore. But I can just wait around for that to get to me, right? I don't even necessarily need that while loop either, right? I can just do a wait, and then that wait inside of that while, and then the while loop right inside of that wait function inside of the semaphore, that'll just kind of wait there, right, until that s value is positive, until I can say, yes, okay, I have access to this. I can do s minus minus and basically reserve control of this one unique lock, right? Then I have my critical section code, that all of that can execute just fine, right? And then I do a signal, right, and I can release back that semaphore, right? And it goes on a loop and loop and loop, right? So this is a very, very simple way to solve the critical section problem just by having a semaphore set to 1 that implies that only one person is allowed to use this resource at a time. So that gets us that problem pretty easy. I think I've already answered the question on the slide, right? If you didn't catch it, right, think about it for a second before. Oh, wait a minute. No, I did not talk about that question on the slide. But so ask yourself that, right? What happens if that lock was initially set to 0? Think about that for 1 second. If the lock is set to 0, then that means that nobody will ever be able to execute any code, right? Everybody's going to be stuck waiting. None of them will get a hold of that lock. Nothing will happen. No progress will be made. So it needs to be at least 1. Shouldn't be more because that means more people can execute in the critical region than should at a particular time. So the stuff I have on the right-hand side is a little bit of a different problem that we've seen before. So here I just want to talk about enforcing order of execution. So the idea is this. Imagine I have 2 threads. One which is executing procedure 1. One which is executing procedure 2, right? So imagine these 2 things are in different threads. And sometimes, right, I want threads to execute things in a certain order. How can I do that? Well, semaphores will give me one way. So here what I want to do is I want to enforce that procedure 1 executes before procedure 2. So let's look at the code. First line in procedure 1 is a printf, so that it'll automatically execute. Okay, that's fine. Glance over at procedure 2. The first line is a wait. It's going to wait on that one semaphore called lock. Well, in this case, what happens, right, is that if I have procedure 1 and procedure 2 running at the same time, one of them will go ahead and do the print, right? The first one will. But the second one can't actually do anything, right? The second one actually has to acquire the lock before it moves forward. Basically, what you're saying is procedure 1 must execute first, right? So it does its printout, prints out the line 1, right? And then it does a signal, right? And that semaphore lock was initially set to 0, right? So that was intended, right, to make that second procedure wait around, right? But then procedure 1 finishes out, signals on that lock. That means that semaphore will become a value of 1, and then the wait in procedure 2, right? Then that'll be able to complete, right? It'll be able to consume that kind of resource, right? And then it'll do that print line 2, right? So in this case, right, we're basically making procedure 1 something that produces the resource. The resource is procedure 1 is done. I know that sounds weird, but that's what it is, right? It's producing the resource. Let me say that again. Procedure 1 is producing the resource that procedure 1 is done. Procedure 2 is consuming the resource that procedure 1 is done, right? That's the logic inside, right? Our purpose, right, our utility, is to make procedure 1 happen before procedure 2, even in a threaded environment, right? Because normally with threads, I don't have any control what happens first. This will force that order to happen how we want it. So this is another interesting use of semaphores, and you can probably do the same thing with mutexes or other concurrency tools as well. So a quick comment here on implementation. So let's say we're implementing our wait and our signal. A good idea just to do this is to say, okay, inside there must be a list of resources, right? It would be better for us, right, to not have that busy waiting, right? So we had in the previous example of the implementation, right, in the very first slide of the section, we said, hey, over when we do a wait, right, that wait will have this while loop, right, and the while loop will run, well, s is not positive, right, and it just kind of sits there and does, nothing, and that's kind of, wastes some time. Well, here's another thought. Maybe what I can do is I can have every semaphore not just have an integer, right, a numbered s, right, that we count up and down, but what if it also had a list associated with it, a list of all of the processes or threads that were waiting for it to happen. Okay, if we had that, right, things would be a little bit easier, right? So let's look at our code now, right? At the top we have this type def being defined, which is basically making a list node, right? We need maybe a couple other variables, but it's basically supposed to be a node on a list. Then underneath that, what I have is my wait, right? And so my wait looks a little bit different. So my wait is going to start out by doing this minus minus, right? Basically saying a resource is being consumed, or maybe I'm just making someone saying, or maybe I'm just making a note that I have a process waiting for it. Second line is where the work happens, right? So then we say, okay, if I am forced to actually wait around, right? If I don't have a resource to give to it, right, to consume, right? If my minus minus gets me less than 0. Well, then that means that, well, I've queued you up, right? I know that I have something that wants to use this resource. I can't actually execute right now, and so what you should do is add that particular process to the list of things that want to execute on this particular semaphore, right? And really it should be a queue, right? We should have an order to how things are waiting for this to become available. And then once I've queued it up, then I can do a block operation, right? I can force that thread to wait until something is available, right? Until that semaphore is increased by 1, until I can do something. Right. So in this case, right, I'm replacing my busy waiting by adding it to a list and then blocking for that thread to complete or that thread to continue only once a resource is available, right? So the performance is going to be a lot better here because we're going for a block operation. Then on the other side, right, we have signal, and then for signal, right, basically if we complete, right, we do a plus plus, right? So we say, okay, that S value is increased, and in that case, right, if we make that so that there is actually something available, well, I can go and I can look at that list. And see, okay, is that list, right, is there somebody waiting around to use this resource? If there is, I can go and wake them up, right? So I'll have whoever is waiting on that thing there for me to talk to and to say, okay, it's your turn to go, right? So this is going to be a better way, just to maintain a list/queue of all the threads that are waiting. If I can't put something on there immediately, add to the list. Whenever I free up a resource, take something from that list. So the last slide here just has a bit of terminology, and we'll use this in a few places. So it is important. All right, so some nomenclature here, right? First thing I want to define is deadlock. So imagine the following. You have two processes, P1 and P2. Each of those processes uses resource A and B, right? Imagine those are two mutexes in your system, two semaphores in your system. And each of those things, well, let's assume they're mutexes. I'll make our example a little bit simple. Two processes, both rely on A and B mutex. Consider the following. A grabs mutex A, P1 grabs mutex A, P2 grabs mutex B. What happens? Well, both P1 and P2 go look for their second resource, right? So P1 looks for B, P2 looks for A. But those resources are held by one of the other threads already, right? P2 is looking for A, but P1 is already holding it. But in that case, right, I get into trouble, right? Because all of a sudden P2 is waiting on something, P1 is waiting on something, but neither of those resources will ever become available because they're held by a process which itself cannot move forward because it's waiting on something that somebody else needs or something that somebody else has, right? So there's a cycle, right? I'm waiting for you to do something, but you can't do it because you're waiting for me to do something, right? So I have no hope of moving forward. Neither do you, right? We're stuck in a deadlock, right? There's a stalemate where nobody can move forward. So this is going to be kind of our primary issue we'll fight with threads, right? Is threads sometimes just get stuck because they can't get the resources they need, right? Because they can't get the mutex or semaphore locks that they need to continue. So this is one bit of terminology. Next thing is this idea of starvation. So sometimes I have a thread that basically it has no chance of ever getting the resources it needs, right? So those two different processes we talked about a second ago for deadlocks, those will actually be in a state of starvation, right? They have no way to acquire the resources they need. This can happen in other cases too, right? So you can have other threads in your system that for whatever reason, they maybe are just never able to acquire the resources they need. Again, that's going to be a case of starvation. All right, a couple more ideas here. First is the notion of priority inversion. So consider again this idea of P1 and P2. P1 maybe is a low priority thread, P2 is a high priority thread. Normally you'd think, oh hey, I have those two threads, the higher priority thread should be the one that runs first. Okay, that's how maybe things would normally work. But then consider this. Maybe both of my threads need the same resource, right? Maybe they both need resource A. And initially, P1, that lower priority thread, has that resource. Well, if it's low priority, then it's basically the system isn't going to give it much compute time. It's going to let other stuff execute first. But hey, P2, right, my second thread, my one with high priority, it also needs resource type A. But there's no way for it to get resource type A until P1 completes, right? Because P1 is the one holding that resource that the high priority process needs. This is a problem. This is what we call priority inversion, because all of a sudden that P1, which normally was low priority, really right now, right, it's blocking a high priority process by holding onto that resource. And so really we want to elevate privileges on that one and make sure that, oh, it'll complete, it'll make that resource available, and then that high priority thread will have a chance to complete, right? So this is what we call priority inversion, right? There is that issue where the lower priority thing is blocking the higher priority thing, and really we need to elevate it. So there are a couple of different mechanisms we could use, right, to resolve this. Basically, the idea here is suggested this idea of priority inheritance, which says, okay, the resource, right, that resource, because it's being asked for by a high priority process or thread, we should say that resource, anybody else that depends on it, should inherit that priority, right? So anybody else looking at resource A, they themselves should have the same priority as P2, right? They should be upgraded. So that lower priority process or thread, right, would be upgraded to match that P2 because they're both using the same resource, right? And they're both using the same resource. I want to make sure I clear the things that are already there, right, that P1, so that P2 has a chance to move forward, right? So we'll call this priority inheritance, right? When we elevate people that are using the same resources as some higher priority thread that is also running.